Now, I've got to say, it's a huge honour to be here today. This is my fourth session that I've been running, and it is also the final session of the day. So I know it's great to see everybody here from TNS, DHA, and also Goldberg and Newlands, and also our foreign guests that will remain nameless. Now, I'm actually really excited to actually introduce John, because John has a wealth of experience in early childhood education, and he has such a passion for it as well. I've spent the last 3 days about science in the early years, but also about inclusion and different subjects as well. So it's been really, really interesting to find out John's journey, how he's worked with the University of Cambridge, but also worked with the University of Durham as well. Luckily, he's never got to Scotland yet, I don't think. But it's wonderful to see how he wants to make science more real, more practical, not like the nonsense that's being taught in most of our schools now that's not changed for the last 50 years. So today, John is going to do a workshop, and it's going to be a very interactive workshop. And for those people who are challenged, shall we say, with their hand-eye coordination, I'm not looking at anyone, Darren, good luck with that as well. However, it's going to give us great exposure to how we can actually bring science to life in the early years, and this will continue not only today, but into the future. So for you guys at TNS, you don't know, he's actually coming to the school tomorrow as well. So it's with a true honor that I would like to on to the stage to please conduct the workshop. Thank you so much.
Assalamu alaikum. Can you hear me when I speak? Because I need 3 arms. If you find it difficult to hear me, then please move forward. There are chairs further forward. On your tables, the people who are on tables are the lucky ones. Well, maybe they're guinea pigs. Maybe we're going to experiment on them. On the tables, you'll find some rulers and some components. And what I'd like you to do with the electrical components, and if you're one of those persons who find it difficult to sit still listening for a long time, this is ideal for you. Can you fiddle around with it and see if you can get it working? Okay, during my talk, I'm not going to be complaining if it totally goes beep. In fact, I'll be really pleased if it does, because it means you've connected it up. I also sent out around the room some of these. Probably you see it in against the screen there. If you haven't seen one of these, it's because these people in the front are hogging them. So if you've got them at the front and you've had a look, pass it back so that everybody gets to see them. I'll come back to that in a moment. Okay, I'm going to give you some research information that's fairly recent. A lot of what we're going to be talking about, we're talking about guardians of the future. I'm going to be talking a bit about the cutting edge of science education and also early childhood education as well. So there are 2 major themes here. And those of you who actually caught my panel discussion the other day will know that I spoke about personalization of education. And what I said was that personalization of education, actually designing your education curriculum for the individual, isn't just an ideal, utopian ideal that we aspire to. It's a reality. It's inevitable. Because whatever you say to a group of children or an individual child, what they learn depends on what they already know. And therefore, it's personalized. So efficiency in teaching and in education is all about trying to find out what it is the child already knows and then building on it. That's the overall issue here. How do you do that with science? And there are some real challenges, as I'll explain. I want to start with this example. It was actually an experiment that was done with children, a vast number of children, from a team in Leeds University back in the 1990s, actually. And they gave this question to children who were 5. They gave it to 7-year-olds, they gave it to 13-year-olds, and they gave it to 15-year-olds. And asked them just simply this: if we take the air out of this balloon on the right, what's going to happen to the balance? They actually didn't show the picture, they actually did it with balloons, so that the child was in no doubt about it. What do you think? What's your answer? You don't need to shout it out, there are too many of us to ask all of you. But I think most of you will probably have a pretty good idea of what happens to it. The 5-year-olds all said, pretty nearly all of them, not all of them, pretty near all of them, said that this side would go up. It would go up because it wasn't so heavy. And it's not so heavy because it's got no air in it anymore. As the children were tested at older age groups, more of them got it wrong. As the children got older, the percentage of children who got it wrong increased each time. So why is that? It's obvious, isn't it? The answer is really obvious. It's got something in it, and we all know there's something between our hands when we do that. It might be invisible, but we know it's there. The other thing that, when I've asked children this question, I've found over and over again with older children, is that they're really uncertain. They worry about it. They say, well, I think I know the right answer. You know, the younger children don't, they just say the answer. Why are they getting anxious about it? I think it's because of learned helplessness. I think our schooling, especially our science education and maths education, teaches children to worry about not having the right answer. And it's this right answer, it's a tyranny of a right answer that causes this helplessness. And they decide they don't like maths, they don't like science, they don't want to do it because the teacher keeps telling them they're wrong when they get an answer. The opposite, as Carol Dweck wrote profusely about, is to have a mastery mindset, to actually approach any problem or any question thinking, I can do this, I can fix it, I can understand this, I'm going to understand it. That makes resilient problem solvers, and that's what we really need in every subject area in the curriculum. We need these resilient problem solvers. I'm going to mention, hardly mention because there isn't so much time, education for sustainable citizenship, sustainability. But resilience is crucial for this age group. Their whole lives are in the climate change era. Ours weren't. We've only just become really aware of it. But their lives are totally defined by climate change. So what do we need to do? We need to draw on knowledge when it's fit for purpose and when it's just in time. We shouldn't be thinking about the most important thing being the knowledge content. We should be thinking about it's the child's problem solving, their understanding, that is the focus of our attention. This is can you all see this? The screens at the back are probably easier for the people at the back, actually. It's an experimental apparatus that was designed to investigate children's exploration. So it's just a lot of pipes, but it does things. So over here you've got a squeaker that makes it squeak when you press it. Over here, if you press that, music. And then there's light that comes on when you press that. So it does lots of things. It's just a toy that was designed for a research project. And the reference is there if you're interested in looking it up. The researchers, first of all, gave the children, one group of children, a demonstration of it, and they showed them one of the things it did. And then they left it with the children to play with. The other group, they went to this toy, they explored it themselves, They touched something, it did something. They said, oh, that's a surprise. And they left it for the children to play with. What do you think the effect on the children was? All the children in the first experimental group were pretty much uninterested. They went over and they did the same thing as the teacher, but then they got bored with it. A couple of them discovered in passing other things, but generally speaking, that was what it did, and that was all they needed. In the second group, where the adult showed surprise and interest in what the thing did, all the children tried pressing and squeezing everything, and they discovered everything there was to discover about it very quickly. Do you see what's happening here? The teacher has closed off the exploration. The children believe the teacher must know if it does other things. The teacher's given us the answer to this particular toy and what it does. It's no longer of any interest. Okay, so we've got some hard evidence here that direct teaching doesn't work very well. It actually stunts children's learning. Now you might think from that, yeah, I'm going to jump that because I've already said it. You might think, therefore, that discovery learning is everything. And I'm going to come back to that in a moment because discovery's got real limitations. But first of all, I want to say something about subject curriculum generally. I mentioned sustainable development, and when sustainable development is defined, mostly you see this model, these 3 pillars, or 4 pillars sometimes, because it's got governance on it as well, involving the people, citizenship. But it's got social, economic, and environmental, and it basically is arguing that you need to actually think about all 3 of those. You need to balance the concerns from all 3 of those for something to be sustainable. It's not sustainable otherwise. And this is UNESCO's definition of what is the curriculum, what we need is a curriculum for sustainability. And they say what ESD requires is a shift from teaching to learning. It asks for an action-orientated, transformative package, pedagogy, which supports self-directed learning, participation, collaboration, problems orientation, inter and transdisciplinary learning, and the linking of formal and informal learning, learning in the classroom and outside as well. All of those things are what we need in order to bring about a generation of children who can actually deal with climate change and biodiversity problems and pollution and all of these things. And the reason is because, well, put simply, the old subject curriculum caused the problem, and the solutions aren't fixed by a single subject. We actually need to get people together to look at different areas, economic, social, cultural, and environmental are just 3 of them, but we need to actually get people together to think across the disciplines and find solutions for it. And this is true in all the different areas. As I said, I'll be able to talk more about this tomorrow when I talk to people about sustainability. I prefer, rather than that pillar, that model with the 3 pillars, I prefer the 3-legged stool, because it's obvious then, if you've got one leg that's shorter than the other, or it's a bit unstable, the thing's going to fall over. It's unsustainable. So I use this model instead of the concrete one. Now, I mentioned discovery, so I've got another little experiment for you to think about. hopefully many of you will be thinking it's something to do with friction, something to do with something you learned about in science yourselves. And I've carried out this experiment. I've shown this to children of different ages. I've even, at the University of Durham, did this experiment with physics undergraduates. They all said that the ruler would fall over. They all said the ruler would fall over. They're physics graduates. So I'm not criticizing you if you thought that as well. That's perfectly reasonable. But what is it about this? What can we draw upon this experience? What can we know from this experience? I think the important thing to know from this experience is the content. The content of all problems, we try to find a simple solution. We try to all hardwired to find the right answer, the easy answer. But actually the world isn't like that. The world is more complex. And seeking the right answer is often going to give you the wrong answer. Mastery mindset is what we need to develop in children. So we need to avoid putting them into a situation where, some teachers in secondary schools, I know for a fact, believe that the children who don't understand their lesson, it's because they're not very clever. And many of the children in their lesson who don't understand the lesson are asking questions that the teacher doesn't know the answer to. And that's why they're doing worse on the examinations, because they've lost confidence. What we need is resilient problem solvers, and we need to give them the experience to do that. This is just at the beginning in education. In the Association for Science Education in England, there are academic papers being written about this at this moment, but it's going to be a long time before we change the school curriculum in this respect. But in the early years, we can do it. We can actually do it now. We've got the opportunity. We haven't got the same pressures of the examination boards, and we can prove that the children will actually achieve more and get better grades if we give them a very positive and empowering education than if we give them this disabling one. So that's what I'm really going to argue about. This screen isn't going to be very big for you, is it? Okay, it's from a book by Fromm, and what is actually showing here is a connection between different things. He's talking about systems. So, yeah, okay, but I can't go back there if I do that. The systems. He's talking about systems. He's talking about how the behaviors in complex systems emerge. They're not in a textbook on the wall. This phenomena, the time that it actually happens when it moves, you can't look it up on a table because it depends on the temperature of the room, it depends on the particular material, it depends on how much perspiration there is in my fingers, it depends on what altitude we're at. It depends on so many different variables that you cannot look it up. There is no simple answer to it. It's an emergent behavior. And most things actually turn out in nature to be emergent like that, including our mind. So what he's drawing attention to is the connection between the Earth's plates. Think about earthquakes. This is how earthquakes work. Can't predict earthquakes. We can model it and we can say it's been a long time since there's been one, but science cannot do that yet. We can computer model it, but we've got no formula to actually do that. So to teach children that this is how friction works is actually misleading them. So you've got friction here, and there are examples like avalanches, sand piles. They move when they're good and ready. It depends on so many different variables. You can't predict the atmosphere, clouds, the weather, climate change. Climate change is an emergent phenomenon. It happens, and we didn't predict it when it was going to happen. And maybe now it's too late. Okay. Does it work? Okay, good. Okay, so we've got, these are all the climate change and sustainability things that we need to think about. And in the last column there, he's drawing attention to the fact that this is how the mind works as well. So when we get a new idea, when we get a eureka moment, and we suddenly understand something that we didn't understand before, it's the same sort of tumbling change, accommodation of our minds that takes place. It's not a simple build-up of facts that lead inexorably to the idea. It's a transformation. That's why it's so much fun. We get excited when we learn something. We often laugh. Oh, why didn't I think of that before? You know, it's an emotional experience to learn something you didn't know before. And that comes with it. So laughter and new insight comes from the same source of complexity. I'm going to give another example in a minute about electricity flow. When electricity flows, I can't hear any buzzers yet. Come on, don't be shy, have a go. Should get a beep out of it sooner or later. But when electricity goes around a circuit, it isn't simply because it works. It requires a certain amount of potential, certain amount of battery energy in order to get it working. And the point at which it starts moving depends on all those variables again. So a simple formula isn't going to actually tell you when that happens. We're talking here about learning generally, learning about new things we didn't understand before. And we're talking in Piagetian terms, we're talking about accommodation. Piaget talked about assimilation, how we learn things and we just fit it into the structure in our minds that we've already got. And then he talked about how sometimes we discover something that doesn't fit. And if we find a number of things that don't fit, then we reorganize our thinking. And that's that accommodation that happens. Forgot what I put there. Yeah, the eureka moment. Okay, both Piaget and Vygotsky, in many courses of teacher education, I know that academics say Vygotsky said this and Piaget said that. Mostly what they said was the same thing. The difference between their theories is quite marginal, in fact. But the massive things they agreed upon. And one of the things they agreed upon was that the mind was an emergent thing. It was a complex system, and ideas were created within the mind as they were accommodated. And their novel properties. One of the implications of this is that you can't take an idea and then break it down into the component parts and expect the child to get it. So let's take a really obvious example, reading. Frank Smith argued this in the 1970s. He said, forget about teaching children to read by just using phonics, understanding the letter sounds, learning the technical requirements for reading. Many of your children will not read just because they can do that. They'll be able to do all those things, but they still won't read. They need something more. They need to appreciate books. They need to be motivated to actually pull together the skills they've learned and accommodate the idea of reading. So it's an emergent system, just the same. So both sides of the argument, the real books, the immersion in language, and on the other hand, the phonics and the learning about letters, neither are true. They're both true. But neither one of them can actually make the change. The only one who can make the change is the child. So the most important thing for children to do, in order to do that, is to love reading, love books. They need to hear books. They need to enjoy books. And then when they've got the skills, they will pull them together to do it. But if they don't, then they won't. They also, Piaget and Vygotsky both argued that learning is a creative process. Now, I'd take that actually further. I'd say learning is creativity, and creativity is learning. I think it's actually quite misleading to have two words for it. If you think about it, when you're creative, you've learned to do something you didn't do before. You know, if you're really creative, maybe you've done something nobody's done before. But It's learning. It's the same thing. And every bit of learning, every child's new discovery is a creative act. Piaget argued it. He wrote a book with this title. To understand is to invent. He's saying that a child, when they learn to read, invents reading. They've invented it for themselves. Doesn't matter if lots of other people have done it. They've done it for themselves. They've invented it. And this was published in 1948. I remember in my teacher education, I was told Piaget never wrote about schooling. He only wrote about psychology. Well, there's a whole book. Emergent learning for Vygotsky and for Piaget is this notion that new learning arrives and you can't break it down into what made it up. Those are necessary, but they're not sufficient to actually create the learning. And both of them contrasted this emergent learning, this new development of understanding, with reproductive or empirical learning. So there are two kinds of learning. One of them's conceptual, if you like. It's things that you really didn't understand before, but now you understand it. And then there's some other kinds of learning which neither of them were particularly interested in, and said, well, that's reproductive or empirical. So we need to think about what that is. Basically, reproductive learning or empirical learning is one-to-one correspondences. So this is a chair. That's a one-to-one correspondence. The word chair fits with that. There's no concept needed. It's not a struggle to learn that. Even a parrot can learn that really easily. This is a shoe. This is my hand. All of those things are purely empirical one-to-one correspondences. And children pick them up from the environment all the time. It's not really what we're interested in here, because there are lots of them. There's another thing, though, and that's phenomena. Children learn phenomena. They learn that when they lift this up, it's got weight. When they let it go, there's gravity that pulls it down. If they're lucky and they're in a nursery where there's water play, then they learn how fluids pour from one thing to another. And they may even learn about capacity and volume from that, especially if you seed the play environment by putting different size containers. They won't do it with all the containers the same size, but if you make them different sizes, they'll see that they can fill up more than one, and they start learning about capacity and volume. If they're lucky, you will have airplay. This is one of the things I promote in the UK, learning about air. There are some children who go to secondary school and a science teacher starts talking to them about the gas laws, about pressure, and they start talking about atmospheric pressure and things like that. And the child's thinking, what on earth is this all about? There is nothing there. It's empty space. They haven't got a concept of air, even teenagers. So you don't really need to talk to make the circuits. You can just do it on your own. They can do it. The phenomena of air can be taught very easily in early childhood, and children will learn the phenomena. What you need to do, of course, is to talk about the upside-down world. If you take two beakers or two containers and turn them upside down and put them in the water, you can empty the water out, just like you can empty the air out, I should say, and it'll bubble out of the container in exactly the same way as you pour the water the right way up. So this upside-down world allows you to pour air from one container to another. And if you just demonstrate that once to a child, they will get carried away and they'll be doing it over and over again because it's fascinating to them. A bicycle pump or a syringe, when they press the end, it bounces back because there's something in there pushing back on the plunger. When you talk to them about kites, why is that staying up there? It's because the air is pushing against it. You know, if you want to give them a really strong understanding of the phenomena, get them outside with bits of cardboard or some flat screen and run. and they run with it that way and run with it flat. And they can feel the air pressing against their hands. So phenomena is very important, and children don't necessarily, just like they don't learn how that ruler doesn't fall, just through discovery, they won't discover everything about air unless you actually have an agenda. So teaching children about phenomena is crucially important. And even though they know that air has bubbles, that doesn't mean that they know that air has capacity. That just like liquids, you've got a quantity of air that you're moving. So there's development, there's progression in understanding the phenomena. And one of the things I want to convince you of today is that that should be the central focus of early childhood science. The good news is that you don't need to know much about science to do that. You just need to think about how does the world work? What are the phenomena in the world that the child is interacting with, and how can they understand it better? Okay, I like to, especially when I'm doing training, I like to put teachers into the position of a child. I want them to feel what it's like when they're just learning something for the first time. So what I've got here is a mind map of a botanist. It's about how a flower works. So it's about reproduction of a flower. And he's written down, he's an expert botanist, and he's written down on this chart all the connections in his mind for botany, how plants or flowers reproduce. If we look at the top part of it here, there are some things here that I know. I've taught, in fact, children to recognize what a stamen is, and what a carpel is, and what a petal is on a flower. Some things about the structure of the flower. But what this expert knows that I don't know is all this stuff down here about the chromosomes, about the particular mechanisms of the male spores and the female spores in the flower, and how this contributes to their reproduction. I know about seed dispersal. I know that seeds are dispersed in different ways by animals and by the wind, etc. I can give examples of that, but I don't know why or what they do when they get to the place they're going to. Notice that most of these things that he's written here, well done, we've got a buzzer working. Most of these blocks are empirical knowledge. Shh. Other people can't hear if you're talking. You should be sitting in the back. The blocks are the naming words. They're the one-to-one correspondences. They're the things you can recognize. You can teach really easily. This is a petal. This is a leaf. This is a stem. What's really difficult are the bits that connect them together. Things like each produces 4, this undergoes, this each produces, each contains one of several, only one grows into. All of those connecting things make it much, much more complicated. That's where the structure of this expert knowledge lies. It's in the connecting things, not in the empirical part. And if we go right to the other end of it, I don't know most of those words even. I've probably come across them, but I didn't actually look up the definitions. I'm not expert enough. And of course, that's true of my education. When I'm 70 years old, I've read a fair bit, read a lot of science, but I don't know this stuff. And you can't be expected in your lifetime to know all the science. So if you simplify it for a child, there's a pretty good chance that what you're saying isn't true. And you're teaching them that something later, they're going to be told, well, that's not right. You didn't understand that properly. And it's your fault because you've taught them. Part of what this is all about is embodied cognition. The fact that it's your body that and I'm running behind time, so I'm going to jump this a little bit. But you've all heard of different neural models. The neuroscience supports what I'm saying very strongly at the moment. And one of the metaphors that is very popular amongst neuroscientists and educators is the fact that you've got these neural pathways that join up different nodes of knowledge. The knowledge is encapsulated actually in the pattern itself. It's the pattern you recognize, but it's the particular pathways that join them together, and those pathways are shown in the mind map as well. This is actually an image from somebody's brain, 1 millimeter squared of somebody's brain, and they've just lit up those particular tracks. And you can see what I'm talking here about, particular patterns. That pattern there could be a cup. And in here, there may be a whole room, and there's a cup in it. And you recognize the cup because you've got this particular pattern that you recall from it. That's how the cognitive scientists understand this. Okay, jump on a bit. What this means in practice is that every child is unique. I think a really good model for a child is like a snowflake. When a snowflake comes down, every single snowflake is totally unique. And that's because the temperature, the moisture, all the constituent parts of it are unique to that particular fragment of water. And that's how children are. And we can't predict what they've learned before. You know, they're vastly different. Or the example I gave yesterday, you know, if you take a group of 4-year-olds in a classroom, some of them are 5, nearly, and some of them are only just 4. That's 20% life difference. That's the same as putting 16-year-olds in with 20-year-olds undergraduates and expecting them to cope. You know, we cannot direct teach this stuff because we're not personalizing it enough. Okay, let's get on to this thing. I'm only interested in this one, nothing else. You've all seen it. What is it? Anybody know? I'm putting you into the situation of trying to put you into the situation of being a child. You're actually learning something from nothing. So what do you learn? Yeah. So, no, it's not paperclip. Yeah. Okay, brilliant. It's actually made. That's correct. It's called a netting needle, and it's mostly, they used to be used to make fishing nets going back, I think, three millennium. There've been some of them dug up in archaeological digs, but they're used regularly all over the world today to repair nets still. Most nets are made by machine nowadays, but you can still repair them with it. So you load it up with the line, and there's a particular netting knot that you use to make the knot. Now, why am I telling you about netting knots? Because, sorry, I'm just going to jump this one. It's because you cannot understand it. Knowledge has 2 parts to it. One part of it is the name, or the object itself, a visual image of it. It's figurative. And the other part of it, the other side of the coin, if you like, is what you do with it. But every nugget, golden nugget of knowledge, doesn't matter what it is, all of them have those 2 parts to them. And if you don't think about those 2 parts, then you're only addressing one. Teaching just the names of things doesn't explain anything to the child. They're not going to be able to use it for anything. It's only if you talk about the operation that goes with it. And Piaget wrote about this, and he distinguished between the 2. He called the figurative part a schema, and he talked about the scheme being the operation that goes with it. And I'm not just talking about objects, I'm talking about everything. Every single bit of knowledge. Even some knowledge you have of creative work or an artwork or a solution to a problem. All of that knowledge has 2 parts to it, if you think about it. And we need to address both parts. Unfortunately, Piaget was French. And when it was translated into English, the only word that anybody used was schema. So it's actually the scheme that is the operation, but most textbooks refer to the figurative part as a scheme, or if they do at all, and they talk about it the other way around. We need to fix that. That's an academic problem. Okay, I want to demonstrate, and I've got 6 minutes, which is impossible. I wanted to demonstrate this point about it being all knowledge, and I'm not going to be able to give you the time to do it. And in any case, as you don't all have rulers, it'd be difficult anyway. Okay, it's a problem to solve, to actually make a platform strong enough to hold one of those cardboard boxes between 3 points. You're going to know the answer to this, aren't you? Okay, bit of a problem there. They don't reach between the two, and you've only got these 3 sticks. So you've got to use these 3 sticks to make a platform just in the middle that's stable. You can't tie it or anything. It's freestanding. What do? If we had another 10 minutes, I'd get you all doing it, but we haven't. Anybody got an idea? I've been really cruel sometimes, and I've let teachers 10 minutes trying this, and they haven't got it. But so I'm being kind now. Anyone? Yeah? If you want a solution, come on then. You're almost there. Yeah. Notice it's the operation here that's defeating. Wait. Oh, yeah. When I've done this before, 2 people have solved the problem really quickly. One of them was a teacher, and they were a Scot. Ian? And they were very involved in Scottish country dancing. And in one of the Scottish country dances, there's a movement where they get 3 swords and they lift somebody up on the 3 swords using this pattern, this interlacing. The other person who got it right away was a child. He was 6 years old, and he'd been to Quran class the day before, and he'd been making patterns of interlacing lines, and obviously that was the image that immediately came to mind. A schema helps you remember something, but the actual solution is an operation. Yeah? So you need both. The 2 sides to a coin. You can't have one without the other. Even the curriculum is a bunch of schemas, and pedagogy are the schemes, is what you do with them. So you cannot have a teaching moment ever that's just curriculum or just pedagogy. They must both be there. So we've got to get used to actually making this point of thinking about both. And the thing is, with young children, the first thing they learn about everything is the scheme, not the schema. Education is constantly talking about schemas, trying to teach children the names of things and the definitions, when really, in the real world, and ever so much in play, children interact with the play, with the world, and say, what can I do with this? What are the affordances? We can thank James and Eleanor Gibson in the 60s and 70s for all the research on that. The affordances are the defining features of perception. So if we start with what things do, then children will be able to build up these structures of the mind. If we start with what they're called, that's not making any contribution to that at all. Did I start late? This says I've got 1 minute 40. Okay, if you were going to use it again, you'd need to remember the pattern, wouldn't you? You'd remember it that way. Okay, turns out that children constantly use very popular schemes over and over again. And researchers in cognitive science, with experimental work, and also practitioners in preschools have noticed that children are using the same scheme habitually. When they've discovered a new scheme, they keep repeating it. So if the practitioner watches what they're doing, they can build on it. They know what it is that the child understands and can make use of it. And some really very, very popular ones, common ones, are connecting things together, positioning things, making a line of things, enclosing things, container. For a young child, a container isn't a cup. A cup is the name of an object, one-to-one correspondence. Containers can be anything you can contain things in. It could be a pocket that your dinner goes into for a baby, couldn't it? Just as much as a bowl. Rotations. Children get totally obsessed with, seems sometimes, with rotations, or transporting things from one place to another. These are the building blocks of all the later concepts. If you think about containment, all of maths is built on putting things into groups or sets and moving them between them. So the confidence that children develop in their early years with containing and all the different contexts of containing, being inside a room, outside of a room, just as much as the beans being inside the bowl or outside the bowl, all of those connections come together to actually develop the child's maths understanding. Okay, I'm going to jump the videos. And in sustainability, these are really important as well. So there are themes that the children can learn at a fairly early age, built straight from those schemes that they're already familiar with. This is what they look like. And they're repeated behaviors. They're easy to recognize. All you need is a repertoire of things you can build from it. Okay, in SchemaPlay, we provide resources for practitioners and for parents to recognize the schemes and also to see some of the things they can build from it that's going to take children to reading and arithmetic and all of the outcomes that we want to achieve later. We've got about 60 preschools doing this in England at the moment. We've just got 34 that have started. And soon we're going to have the hard evidence that shows that the outcomes come from this as well, and it's not just doing the right thing, it actually works. It actually makes a difference. And it comes from the theory. I mean, it's a reinterpretation, a re-look at many of these ideas, but it comes from theory. I'm going to give you a really quick whistle tour of the principles of what could, because I mentioned electricity, and electricity is on the table. I should be pointing that way, shouldn't I? Oh, this is, for example, the teacher responding to positioning. So she sees the child is positioning some of these wooden dolls, and she thinks to herself, I can extend that. I can put them with other colors so they can do some matching. Or she thinks, I've got some graded dolls in the cupboard. If I give them those, they can start doing grading. That gives you number, that gives you a measurement, it gives you so many other things. These are the skills that the practitioners need in order to build on them. And they're responding to the child. So the child is freely playing all that's happening, and it's very much like Montessori. This is intuitively Montessori got this, I think. She didn't theorize it. She didn't have the theory to be able to do that, but we can now. And the theory, the latest research shows that this is exactly what happens. In the brain, we know that the motor neurons fire up when we see something, or hear it, or even when we think of something. And it's actually the act of clapping that makes us recognize the sound of somebody clapping in the next room. So, you know, all of these things with neural imaging, we can actually experiment now. And it explains so much. Okay, I said electricity. Jump to an electricity slide. What we did was to try to build electricity into the education of a group of 3 and 4-year-olds. So electricity is ubiquitous. It's all around us. It's like food and water. You know, we depend on it. Why the hell are we teaching children about it? You know, it doesn't make any sense. So for sustainability, we need to teach children about turning things off and conserving energy. So it makes it really necessary. So that was the context in which we did it. And nearly all of you, I guess, your first introduction to electricity was to make a circuit and maybe test things that were conductors and insulators. Is that right? Yeah. It's totally untrue. All of that you were taught is actually wrong. It's not good science. The whole world does it. It's not just your teachers that got it wrong. Here's a buzzer. It's a little bit more sensitive than the battery and the buzzer you've got on your table, but it works in exactly the same way. If I connect the wires together, it makes a buzz. And if I don't, it doesn't. But the difference between this one is that if I hold them, the electricity goes through me. And you can hear that it's not very much electricity, but it's going through me, which proves that if I touch some electricity, I'm going to get electric shock. And it could hurt me if it's a lot of electricity. So when you were taught that I'm an insulator, you were taught that electricity is safe, basically. This teaches children that it's not at all. If I put it into water, I forgot to bring a cup. Has anybody got a cup? No? Okay, I'll resort to the only fluid that's to hand, my tongue. Water conducts much better than I do, my skin. So water is really dangerous with electricity. So don't ever take any electrical device into a bathroom. This is a systems approach. This is an emergent approach to electricity education. The old reductionist one simplified it to the extent that it just wasn't true anymore. And it's misleading. It's teaching the children to be helpless and to be puzzled. And it's also, you know, it's something you have to undo later in education, which makes it even worse. Who was hoping that I might be talking about information technology today? Put your hands up if you were. Could you give them a book? If you were, could you give them a book? I'm sorry, I haven't had time to do it. I wouldn't have had time in an hour to look at all of it. So I haven't given you any ICT, but I've got a booklet that's, no, it's out of print, but I've got a few copies here and you're welcome to take it. So if anybody wants something on IT, those are coming out. If you have a real interest in this and you want to develop it further, then come and see me. I've got some resources with me that I can give you. But there's an awful lot on the internet. If you go to my web page, which is johnsb.org.uk, you'll find many publications that are free to download and cover this ground further. I said I'd show these quick slides to show the children. There's the battery and bulb. By the way, the components you've got on your table are problematic. The thing that lights up isn't a bulb. It's a light-dependent resistor, which only works if you put the electricity through it one way. So you don't want to use that with young children. You want an old-fashioned filament lamp that works both ways. Otherwise, you're going to confuse them. Okay. The other thing you really need when you do this with children is connections that they can manage. And wrapping wires around is too difficult. They need crocodile clips to actually hold things together, and those are available from school suppliers very cheaply. I said I'd show you some children, so let's do that. Oh. The energy story is the important thing, so we've got various analogies to teach electricity, but this is what we're trying to avoid, telling the children that what you learned yesterday is no longer true. This particular box is something that I developed just for this purpose, and it's not on the market at the moment. But this is, and it does exactly the same thing. It's called an energy rod, and it costs about, what would it be? It's about £14. What's that in rupees? But it does all the same things. It makes a circuit go through water, etc. Okay, so the children were given a buzz box to play with. They were given things that would support them because they already had rotations. They were already playing at moving things around and being really interested in wheels and things like that. So we really focused on circuit. Think of the word circuit. An electric circuit is a circle. So it's an easy one to remember. And the first thing they did was to make a circle themselves and pass the electricity through. And very quickly, they discovered that they could have an on-off switch by pressing their nose. So if you press somebody's nose, it beeps, which was great fun. As you can see, they're really enjoying making circuits. And they're getting this concept of rotation in electricity really strongly from an early age. Then we gave them something really basic. It was modelled on the electric in their home. So it's a light switch. It's got a small bulb and a small battery so that it's safe, that they could play with in their play area. Free play apparatus. Quite soon they discovered they could connect things across the bulb and drive other things. One of their favourite things was electric motors. So the children started wiring up electric motors and making fans. Remember, these are 3-4-year-olds, and they're making electric circuits competently, no problem at all. They did have problem with the crocodile clips because their finger movements aren't strong enough at that age, generally speaking, but they persevered. They really carried on until they could connect it up because they were so motivated. And that, of course, strengthens their hand movements, which is a brilliant thing for their writing later. And many other things. The teachers taught them about electricity. They went outside and looked at the electricity coming into the house. So they're making the connection between it. Not so that they understand electron flow, because that's another one. You might have been taught that electrons flow around a circuit. They don't. Electrons do move in a wire, but only a little bit. And they'd go around a circuit in about an hour if you had it connected up to a buzzer. It's the charge that is moving through the circuit, like a wave going through water. That's the physics of it, but it's simplified to the extent that it's not true. If you make a circuit through water or salt solution, it's not even electrons that are moving through. The atoms actually move. They're ionized. They're positive and negative ions of atoms that are moving. You can't teach young children this. You can't teach children of 14 that competently. It's undergraduate physics. So what can you teach? You can teach them about the energy flow. You can teach them about circuits, about connecting, rotation, all of those things that will allow them to understand these things later. And more importantly, use them. They'll be able to make the circuits. This child's got a battery. It's actually full of water. So it's a water battery. They're pouring water in the top, and then they've got a little windmill at the bottom, a water wheel at the bottom that's driven by the battery. So they've got an analogy of the energy being used up in the battery and driving something, making the motor turn around. And you can buy these in school suppliers. It's a little motor with a turbine on it and a light-emitting diode, so it lights up when it goes round. And of course, batteries are so important to us now. We're actually, in England, trying to make lots of reservoirs so we can pump water up onto mountains during the night time when nobody's using the electricity, so that when they are using the electricity, it comes back down and drives the generators. Because at night time, the solar panels don't work. So batteries, hydro batteries, are real and they're big, and children of 4 can understand it because they play with it. Okay, so recharging, using rechargeable batteries, so the children get used to the idea that sun can be converted into energy for batteries. All of that is really important for sustainability, and it's perfectly accessible to 3 and 4-year-olds. Don't have to wait, we can do it right away. And if we look at those children who are involved in that particular, this is a published study by the ASC. We started with the rotators, but then the children who already were positioning things and connecting things together went way ahead of the other ones. They were ready already to stretch it further. So it's just a matter of monitoring the schemes and building on them. I'm sorry I've gone over time. I will stop there and I'll release you. Those of you I see tomorrow, please, come with your questions. If anybody's got questions now and needs to get away, then please use my email address. It's johnsb@gmx, and .com, and I will answer, I promise. Thank you. John SB, so it's JOHNSB @gmx.com.